Hello, we are Hyuck and Pertin Guining. Our topic is flapping wing air vehicle. The goal of this project is to develop a flapping drone so that it can follow the desired path and avoid obstacles. For this purpose, it was designed and go through a simulation, and finally obstacle avoidance flight with path planning was performed. For flight simulation, we have this dynamic model for flapping drone. The equations of motion are 6 DOF nonlinear equations for translational and rotational motions. The aerodynamic model is modified strip theory. This model considers the wake and the flow separation effects caused by flapping wing. In simulation, the aerodynamic forces are generated by this model. PID control is applied for longitudinal control. Flight speed can be changed through flapping frequency, and the diagonal angle is used for the altitude. In lateral control, side slip velocity and direction angle are main factors. Each of them is controlled by adjusting flapping amplitude and folding angles. These are the path tracking flight videos. As you can see, it can follow various flight paths such as helical or swinging path. The location is measured based on the distance between anchors and the tag. For this purpose, an ultra-wideband communication was used. Flight performance was verified through flight test. When the flapping frequency is 3.2 Hz, the average flight speed is 3.7 meters per second, and it could descend altitude by gliding state. Next is circular flight performance. The turning radius is 3.7 meters and it can turn smoothly while maintaining its altitude. Considering the dynamics of the flapping drone, a random path can be generated for each step. It can reach the final goal through this kinodynamic planning.
Hello, this is Guining, and I will be explaining the motion planning algorithm we wrote for our system. Since our flapping bird is quite light and it cannot use onboard sensors or the usual motion tracking systems, we have considered using an ultra-wideband tag or UWB tag as the object. This can emit spherical wavefronts that can be detected by our flapping bird, and think of it as a spherical obstacle, which is what we used in the simulation. Our motion planning algorithm uses the potential field method, where we can find the gradient of the current at the current position, considering the attractive and the repulsive effects. Given the current gradient, instead of using the magnitude, we use only the orientation of the gradient to find the next position we need to go to. This is done because our robot or the motion planning algorithm maintains a set of constraints regarding the robot's turning angle, pitching angles, and velocity. Given the set of waypoints, we finally prune the path in order to make the waypoints come at constant distances from each other and make the waypoints way clearer. So the algorithm can run on a real time by calculating the gradient at the current detected position. But here we decided to find the set of waypoints completely and then run the simulation. When the simulation is run, this is the path that we find, where the robot is avoiding all the obstacles and then reaching the goal position. If we look at the path that has been generated, we see that it follows the constraints of the robot by not running very sharply and also avoiding all the obstacles while generating waypoints at constant distances. Thank you.